Now, the special thing that's happening is to do with CPT symmetry.
Great.
So CPT symmetry is charge conjugation, parity, and time reversal, which basically means that you take the conventional description of it is you take the coordinates in space-time, which we think about as numbers. There's the time coordinate and 3 space coordinates, and you replace them with minus themselves. Now, probably the nicest way to think about this is if, in effect, you are rotating space into time. Okay, so if I think of time going up and space going sideways, you do a rotation by 180 degrees, so time goes down and space goes in the other direction. So that is what do we call a PT transformation? It's parity, reversing space, and T, time reversal, reversing time. Now, in special relativity, you're not allowed to rotate space into time. Okay, we're allowed to rotate space into space because we see that the world is pretty much invariant under rotations in space, but you can't rotate space into time. Why? Because in special relativity, you're only allowed to boost, meaning you can travel faster, and that has the effect of squishing space and stretching time, but you can't actually rotate them into each other. Now, again, this comes into the mathematics of complex numbers. So it turns out that in particle physics, when you calculate scattering of particles or any event involving ingoing and outgoing particles, you are allowed to rotate space into time, and that's a exact symmetry. So one of the most famous, expositors of quantum field theory is Sidney Coleman. And he has this beautiful book. His lectures at Harvard are sort of a classic, and his students wrote them all up. And they're the best place to learn about CPT, by the way. And Sidney says, look, if we discover in an experiment that charge conjugation is violated, when you change a particle into an antiparticle, you discover that physics changes. That's no big catastrophe. If parity is violated, inverting space is not an exact symmetry, that's not a catastrophe. And same for time reversal. The laws of physics we know do actually violate time reversal, space inversion, and charge. Each of them is violated separately. But, he says, if CPT is violated, that is a complete calamity. We would have to start all of physics again. Okay? So CPT is very profound. Now, it changes particles into antiparticles. And the nicest way to picture this geometrically was realized by a guy called Stuckelberg in 1941. And so he was a genius in Austria who was not sufficiently recognized in his lifetime. But he realized that if you think of space and time, so time goes up, space goes sideways, and now think of a particle. What's a particle in space-time? So a particle is what we call a world line. So this particle is a curve, every particle follows a curve through space-time. So if I slice the space-time in the time direction, I'll see this point moving along in space on different slices, as the slices proceed. So Stuckelberg said, okay, that's the picture of a particle in relativity. And in classical general relativity, it can't go faster than light. And that always means that this line going up in time, if the particle is stationary, the line just goes vertical. But if the particle's moving, it goes at an angle to the time axis, because moving along in space. It's not allowed to go faster than light, so it can't. The slope can never be bigger than 45 degrees from the vertical. And so Stuckelberg said, wait a second. In quantum mechanics, we have processes called quantum tunneling, and they allow things which are impossible classically like particles going through walls, but they're perfectly possible in quantum mechanics. He said, even though classically a particle can't go faster than light, quantum mechanically, surely it's not disallowed. So he said, what happens if I have a particle which is traveling forwards in time, okay, and then it gets faster and faster, and its world line tips over, and it ends up going backwards in time? And he said, that's got to be allowed by quantum mechanics. And he interpreted. He said, you see, when it's going forwards and we do our time slices, we will see a single particle going up that where the line intersects the plane. But when it comes back, we see another particle, except it's going backwards in time. And that's an antiparticle. And Stuckelberg realized that quantum mechanics and relativity inevitably predicts that for every particle, there is an antiparticle. And the interpretation is that an antiparticle is just a particle that happens to be going backwards in time.
Yes, many people attribute this to Feynman.
Yeah, that's not right. Feynman got the idea from Stuckelberg.
All right.
And Stuckelberg left so-called fundamental physics and worked on chemistry, mainly because his work wasn't appreciated enough. But as time goes on, you will find him mentioned more and more and more often. He had incredibly deep insights into what we now call quantum field theory, actually long before Feynman.
Wouldn't that also show a particle disappear? Oh, no, but that's right. If there was a particle, antiparticle, right.
Yes, so the interpretation of this funny curve up and down is that our interpretation, our picture of it as time proceeds, is we see a particle and an antiparticle, and they come along and annihilate. And we see that in laboratories all the time. And likewise, you can have a particle coming in from future time and turning around and going back up again. And that's pair creation in an electric field. If you switch a strong electric field on, then it literally pulls an electron out of the vacuum in the direction opposite to the electric field, and it pulls a positron, a positively charged electron, or the electron's antiparticle. It also pulls that out, and the two together go flying apart. And Stuckelberg said, this is inevitable. You can have this process. Now, in fact, the particles annihilating and the particles being created, the pairs annihilating or being created, those are CPT conjugate processes. If I just turn the picture upside down, which is the CPT transformation, the one is exactly the other.
Yes.
So the rates of them have to be identical. And that's the CPT theorem. So our picture of the Big Bang is in fact completely the same mathematically as a particle-antiparticle pair being created. We have these two sides of the Big Bang, something, our universe coming out of the Big Bang, and then on the other side, the CPT image or anti-universe. From our perspective, it's going into the Big Bang with a sort of reverse direction of time, but from its own perspective, it's just the same as ours. And so we see this happening in physics, the consequences of CPT symmetry happening in physics we absolutely know and trust. And all we have done is generalize the same mathematical principles to cosmology and now to black holes. Now, to come back to the black hole, when you fall into the horizon and you hit this special surface, what's going to happen? Well, what happens is very dramatic. As you fall in from this side, the other side is part of the anti-universe. And so there is antimatter. There's an antimatter version of you falling into the other side at the same time. And both of you will hit the horizon at once. And what will happen is the particles you are made of and the antiparticles the other the other version of you is made of will annihilate into radiation, and that will travel up the horizon and eventually escape when the black hole evaporates. So it is a complete picture, not only of formation of what black holes are, but of how they can evaporate and where the matter that forms the black hole ends up, which is it just annihilates into radiation and runs off to infinity. Now, I have to say that only the first part of the story, the stationary black holes, so this would be Schwarzschild, which is not charged or rotating, or charged black holes, exactly the same thing works, or even rotating charged black holes, which are the most general case. We've shown that mathematically they all have exactly the same property. But what we have not shown is that in the time-dependent black hole case, a black hole actually forming by a collapsing star, and then evaporating, that's a much harder problem to describe. And so we're working on this, and basically this requires new approaches to solving the time-dependent Einstein equations, which still need to be developed.
I see.
So this is still a work in progress, but it's very exciting because potentially there would even be signals of this matter-antimatter annihilation on the horizon.
Uh-huh. So your innovation and your collaborators as well wasn't just analytically extending.
Right.
Okay, because that's been done since the 60s, as you mentioned.
Yeah, no, but the funny thing is that this particular way of analytically extended preceded the work in the 60s. As I said, Einstein and Rosen used it. But they, of course, only did Schwarzschild, the simplest solution that was known then. What we've done is use actually the same analytic extension, but we've applied it to all possible black holes. And we find it still works. And so I think the fact that there was an alternative was not noticed by people in general relativity because they were insisting that the metric has to locally look like Minkowski space-time at every point in space-time. And that does not happen on the horizon. On the horizon, you have this funny... Technically, you say that two of the eigenvalues switch. That's what happens on the horizon. The time-like one becomes space-like, and the space-like one becomes time-like. So they both go to zero on the horizon. So something, let's say, different than normal GR, general relativity, does happen on the horizon mathematically. But to us, it seems like this is easily the most minimal resolution of all the puzzles associated with black holes. Our whole philosophy is that we shouldn't overcomplicate physics. We need to always look for the simplest, most minimal resolution of the most profound puzzles. So, what was the Big Bang? We claim we can understand that by this process of analytic continuation. And there's some new developments on that front too. When dealing with black holes, we would say that the conventional description has these pathologies, that you lose information, that you have a curvature singularity, which is just unremovable. It means the theory fails irredeemably. Finally, actually, the conventional description is inconsistent with CPT. It's just inconsistent. And actually, Stephen Hawking, the last paper he ever wrote on black holes, was called something like the black hole information loss problem and weather. Okay. It was a funny paper. It was about, he was trying to explain that if black holes evaporate, the information gets scrambled. And it's more like the weather. We can't predict the weather tomorrow, but that doesn't mean we don't believe the equations. But during this paper, he explained that one of the basic paradoxes with black holes is they seem the usual description seems to be incompatible with thermal equilibrium. So what is thermal equilibrium? Thermal equilibrium is where you have stuff, let's say in a box, and it's hot. And so if it's molecules, they're flying around at high speed and interacting with each other. and there will be radiation that's bouncing off the walls of the box. This is a very generic physical situation, that you have hot stuff in a box and it's fluctuating into all kinds of configurations. So imagine you put a black hole in this box. Well, CPT symmetry demands that for every process forming a structure, like forming a black hole, you're inevitably going to form black holes out of, matter happening to fall in towards itself. So every process in which you form something, there must be an exactly equal process in which it unforms. That's what CPT symmetry says. Whatever comes in at whatever rate, there must be an exactly mirror image process where stuff comes out and unforms that structure. Now, in the usual description of black holes, that's impossible, because stuff falls in and forms a black hole, and that's the end of the story. I mean, you can't unform the black hole. So he said the conventional picture of a black hole is incompatible with CPT, because we don't have white holes. There's a black hole where things only fall in, but there is also a white hole solution where things come out. Mm-hmm. And the problem with the usual description is that we ignore the white holes, and we only include the black holes in our description of thermal equilibrium. And Hawking said that just doesn't make sense. So our black mirrors, we believe, are perfectly compatible with CPT. That's how we construct them, and therefore they're perfectly compatible with thermal equilibrium. So they seem to have a number of advantages, but as I mentioned, a lot remains to be done to understand when such a black mirror actually forms. What is seen from the outside as it settles down, or in particular, if two black mirrors interact. It's a very tough problem. And there's such exciting progress, in the last, 20 years, because now we can literally see black holes merging, and as they spin around each other, they emit gravitational waves, and we see them actually merge into a bigger black hole. So all of this stuff is now possible to watch happening. In the next few years, there will be literally movies of black holes merging, because the gas which surrounds them is like a tracer. And so we can see the gas with radio telescopes. And so with powerful enough radio telescopes, we can actually see all of this amazing physics happening. So that problem of understanding exactly how two black holes merge was only really solved about 20 years ago, using powerful computational techniques and supercomputers. You can put Einstein's equation on a computer and see what it predicts. But that's the prediction from the conventional picture, and includes the black hole interior. In our prediction, you basically need what is called different boundary conditions on the horizon than the ones people would normally use, and those will change the evolution of the black holes. And so that's going to take some time to sort out. It's a harder problem to solve than the conventional approach, because in a certain sense, we are putting in a boundary condition in the future as well as the past. You see? You'll notice that when I turn space-time upside down, the future becomes the past, right? And that's one of the appeals of our cosmology picture, is that we claim that the arrow of time emerges in this picture, because on the two sides of the Big Bang, you've got time going in different directions. So time goes forward out of the bang on both sides.
Yes.
And somebody inside the universe, would see only one of those two arrows. And so we claim that the arrow of time emerges from a Big Bang within this CPT symmetry picture, and doesn't have to be put in from the outside. In conventional approaches to physics, the arrow of time is just put in at the beginning with no explanation, even though the laws of physics don't violate CPT, which includes time reversal, people just assume that the state of the universe somehow does violate CPT. Now, when it comes to solving these two merging black holes, usually people would specify the configuration of the black holes at one time and then just run the equations forward to see what happens. But in a CPT symmetric picture, it's a little more involved because what you have to do is impose conditions, not just in the past, but in the future.
Now, why wouldn't it be that by imposing conditions on the past, it automatically imposes conditions on the future if they're symmetric?
Good point. That would be true classically. Okay. But in quantum mechanics, quantum mechanics is very different than classical mechanics in the way it treats the past and the future. In classical mechanics, the world is a machine. You just specify the configuration, like the particle positions and momenta at one time, and just run it forward. In classical mechanics, you cannot specify the complete state of the system at two times. Not allowed to do that. I mean, if I tell you what the positions and velocities are now, you can't tell me, oh no, they would, I'm going to freely specify them at some later time. It's inconsistent because it won't agree with the evolution of the initial condition. But in quantum mechanics, this is not true. In quantum mechanics, you are free to specify the wave function at two times. And so I can tell you what the wave function is at one time. You see, it's only a function of the coordinates.
Right.
And I'm not allowed to tell you the velocities if I told you the wave function of the coordinates. So if I tell you the coordinates, so you can either specify the wave function of the coordinates or the wave function of the momenta. You can't do both. But the upside of that is I can tell you what the wave function is at one time, arbitrarily, and I can tell you what it is at a different time, arbitrarily, and then I can predict what happens in between. And this is a point made by Yakir Aharonov, who's probably the deepest thinker on quantum foundations today. And in fact, all he does is think about paradoxes and puzzles and thought experiments. And he does it better than anyone else. And his point is that in quantum mechanics, it's very natural to have two times. Our point is that allows you to impose CPT symmetry on the universe, because you say, I take my initial wave function and my final wave function, and CPT symmetry asserts that they are identical. And then I just figure out what happens in between. And we live in between, and we can then predict everything that happens in between.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.